As we begin to talk about empirical rate laws, this is now laws versus just how to calculate a rate, but how does that rate relate to the reaction? So the pattern of how a rate changes with its reactant concentration, we're going to call a rate law. And we're going to have two kinds of rate laws: differential rate laws, which is this part, and integrated rate laws. So it turns out that all of the reactions will follow a pattern. The rate is related to the concentration of the reactants, and it can change in different orders. So given a reaction of A plus B makes product. So it has two reactants. It could be three. We extend this idea. Sometimes it's just one reactant. The rate is going to be equal to some rate constant K times, for every reactant, its concentration raised to some power. So in this case, if we just have two reactants, A and B, it would be K concentration of A raised to the N power. That would be for A, and concentration of B raised to the M power. That would be for reactant B. So these N and M's, these exponents that are the pattern of how the rate changes with the concentration of that particular substance, are called orders. And to differentiate which one we mean, we say order with respect to A, or order with respect to substance B. So the order with respect to is a particular reactant. So N and M don't have to be the same number. They can have different patterns or different orders based off of different reactants in the reaction. Now, if I wanted to know for the entire reaction, what is the order? Sometimes they use the word overall order. Sometimes they just say reaction order. I'm going to sum up all the individual reactant orders. So in this case, it'd be N plus M, but if I had a third reactant, I would have N plus M plus then the order of that third reactant as well. And then I have this rate constant. The rate constant units will change depend on the order, because in the end, the rate has to have units of molarity per second. And so K's will change how many molarities it has, that it has to cancel out of the N and M orders. It comes out to that. So sometimes the reason I point that out is that the units of K can sometimes tell you about the overall order of the reaction, and that can be useful at times. Now, how do we find out the specifics of what are N and M and what are K? That we're going to have to do experimentally. So let's talk a little bit more about some common, so the three orders that we're going to deal with are going to be an order of 0, an order of 1, or an order of 2 with respect to a reactant. So this is not overall order, this is order with respect to a reactant. So it turns out we see some general patterns. And in this case, we're just looking at the order compared to the concentration that it affects. So I have some concentration of a reactant and time. So if I look at what happens to the concentration of the reactant over time, if it is 0th order, it continues to decrease, but at the same rate the entire time. Remember in that last section when we talked about how to calculate rate, we know that it's related to the slope of the curve of concentration versus time. And in this case, since it's a line, the slope is constant. So it would be the same rate the whole time. It's independent of concentration of A. If it's first order, it turns out that as there is less and less concentration, the reaction rate slows down. So I see a very steep beginning. At first, the reaction rate is fast, and then it slows down. The same thing is true with second order, except it slows down more quickly, because now it's affected by, it's the concentration squared is the pattern. So we see that in general with these, if it's first or second order, as the concentration decreases, the rate slows down, which kind of makes sense. There's less of it. All right, so what if we look at a different graph? And we're going to see a lot of graphs in this chapter, and it's really important to look at what is on the axes so that you know what kind of graph it is and what kind of properties and generalities you can get from it. So if I'm looking at a rate versus concentration, in other words, how does the rate change as a function of concentration? This is essentially the rate law, right? Because rate equals something times concentration to the power, and so this is looking at it. So if it's 0th power, something to the 0th power means A to the 0th power is 1. Anything to the 0th power is 1, which means The rate has nothing to do with the concentration. The rate will be some rate and it'll be the same no matter what. So if I have a rate versus concentration and I have a horizontal line, the reaction is 0th order with that respect to that reactant. And if I have a first order, it's going to be the rate is proportional to the A to the first order, or just proportional to the concentration of the reactant. And so I'm going to get a line. So the rate does change, but it changes proportional to how much concentration of reactant we have. And then if it's second order, I get something like an x squared plot. You know, I get kind of parabolic, half of a parabola. And that makes sense because it's a concentration squared. So as the concentration increases, the rate increases more and more quickly. So it doesn't increase at a constant rate, it increases at a squared rate. Notice that in a reaction, we're not increasing the concentration of the reactant, we're decreasing it. So normally what would be happening is we would start with a high concentration and go down to a lower concentration as the reactant is used up. So normally the rates of reaction are going to be decreasing over time, which we see over here. All right, so now let's kind of write those down, not in graphical form, but just in list of properties. So for 0th order, again, the rate is going to be constant. It's independent of the concentration of the reactant. If I have the concentration for time, I get a line. If I have a rate versus concentration, I get a line. And it's a horizontal line specifically, not just any old line. So the big thing that we'll tend to do and use as a quick check is what happens if I double the initial concentration of the reactant, and I measure the initial rate. So if I double the initial concentration, nothing happens because it has no dependence on the concentration of A. And the units would be molarity per second. If it's first order, again, the generic rate law would then be rate is equal to K times the concentration of the reactant raised to the first power, or just K times the concentration of the reactant. The rate is going to slow down over time. Concentration versus time will be a curve, and the rate versus concentration will be a line. If I double the concentration of the initial concentration of the reactant, it doubles the rate. And my K would have units of inverse seconds. If it's second order, again, rate is equal to K times concentration of the reactant squared. The rate is going to slow down with time, but more quickly than a first order. Concentration versus time is also a curve. The difference between first order and second order graphically is that if I have the rate versus the concentration, I get a curve, not a line. And if I double the initial concentration of the reactant and I measure the rates, it's going to quadruple the rate. So I can see that, you know, if I double 0th order, no rate change. Double the initial concentration for first order, I get a double the rate change. And then the doubling the concentration of a second order, I get a quadruple effect in the rate. And my K units for a second order is inverse molarity per inverse second, or inverse molarity inverse second. All right, so how do we actually go about finding M and N and K? So one possibility is using this method of initial rates. So I'm going to run this experiment many, many times, and I'm going to keep changing the initial concentration of the reactants, and I'm going to measure the rate. Specifically, I'm going to measure the rate constant. I'm going to measure the rate, and I'm going to measure the rate. So if I take my generic rate law, rate is equal to K times concentration of A to the N, concentration of B to the M. Now you could extend this if it was 3 reactants. This would be a 2-reactant reaction. And I take that formula and I make 2 versions of it and take a ratio of it. It turns out mathematically I get this equation. The ratio of the rates is equal to K times the initial concentration to the nth power, initial concentration to the nth power. So look what happens when I make a ratio. The K's, first of all, are going to cancel out. So now I've lost one variable, which is good because I need to only be looking for one thing at a time. Also, look what would happen if I look at this equation. If I see that I have concentration of A initial over concentration of A initial in a different experiment, if the concentration of A in both of these experiments is the same, then these are going to cancel out. It doesn't matter what power N is because this ratio is 1 and 1 to any power will still be 1, which means then I can make it dependent on just one reactant. So I'm showing you two specific versions of this. So if I choose a case where the initial concentration of reactant A is different, but the initial concentration of B is the same, then the B portion of this drops out, and I get that the ratio of rates is equal to the ratio of the initial concentrations raised to the nth power. Now, I have a power here, and that gets a little tricky. We're going to normally just use doubling, and that makes the math easier. But if I had the initial rates were different, but they weren't doubled, I could use logs and solve for this, and that the order would be equal to the log of the ratio of rates divided by the log of the ratio of initial concentrations. Again, we're normally going to use this version over here on the left. Now, that's finding N, which is the order for reactant A, but I also then need to find M, which is the one for reactant B. So I look for a different set of trials. This case, I'm going to keep the concentration of A the same. It will drop out of the equation, right? If these are the same, this drops out, and I'm just left with the ratio of rates is equal to the ratio of initial concentrations of reactant B raised to the nth power. And again, if I take logs of that and rearrange it, I get this, that I could find the order directly from a ratio of logs of the rates and of the initial concentrations. So I find N, I find M. Now I go back to this initial equation. So I take one of the trials. I know its rate. I know the initial concentration of A. I know the initial concentration of B. I've now found N and M. I now have enough information to find K. So now I find K. So now at the end, when I'm done with this, I have K, I have N, I have M. Now note that if this was a two reactant reaction, I would need a minimum of 3 experiments to do this. One in which A was changing concentration, but B was the same, and another in which A concentration was the same and B was different. And I'd have to measure the rates for all 3 of them. So you tend to get a big table with like a whole bunch of different rates. All right, so how do we get rid of the logs? Turns out I can just use some simple, nice tricks about math. If I use a double the initial concentration of a reactant, then this ratio of the initial concentrations is 2. And now this becomes the ratio of the rates is equal to 2 to the n power. Remember, we were talking about what happens if you double the concentration, initial concentration. This is what we're referring to. So I will do the experiment in such a way that I double the initial concentration of a reactant, but I leave the other initial concentration of the other reactant the same, which means I get this relationship. Now this is easy. The ratio of the rates, I get a number, but if n is 0, 1, or 2, the math is easy. If n is 0, 2 to the 0 is 1, so the ratio of rates would be 1, or unaffected. If the order is 1, 2 to the 1 is 2, so the ratio of rates would be 2, it'd be doubled. And if the if the order is 2, 2 to the 2 is 4, so the rate would be quadrupled. So this is typically how we will run the experiments. Note over here, you see, we ran the experiment with 0.1 and 0.1 and then measured the rate. But then I doubled NO2's concentration, but I left CO's alone. And then I did a different experiment where I left NO2's concentration the same, 0.2 and 0.2, but I doubled CO's concentration and I measured the rate. And then I did another one where I quadrupled from the original one, I quadrupled the initial rate of NO2, and one where I left CO concentration alone. So note that for finding N, the order with respect to NO2, I'm going to look for 2 where NO2 is doubled but CO stayed the same. That would be trials 2 and 1. So I'm going to use trial 2. I usually always use the bigger number on top. It just makes math easier. So the bigger rate over the smaller rate equals then it would be for that same, for trial 2, it's rate over the initial rate. And then I'm going to use the initial concentrations of NO2 over NO2 for trial 1. So this ratio of the rates ends up being 4. So we know it's second order, but that's okay. Keep going on. The ratio of NO2 is 0.2 to 0.1, or 2 to the n, 4 is equal to 2 to the n has to be 2. 2 squared is 4. So I know now that the order with respect to NO2 is 2. Now I'm going to do a different set of trials where NO2 has stayed the same, but CO has doubled. And that would be trials 2 and 3. So I'll put 3 on top, 2 on bottom, because 3 has the higher rate and 3 has the higher initial concentration. Okay, so then I get the ratio of rates. Note that the ratio of rates, it didn't change. It's 1-ish. I mean, it's 1.01, but let's just call that 1. It's close enough. And the ratio of initial concentrations is 2. So I get the statement that the 1 is equal to 2 to the m. Well, then that means m has to be 1. Or it has to be 0, because the only way 2 raised to any power would be 1 would be if m is 0. So now I know n, I know m. I go back to the initial rate equals k times a to the n, b to the m, and I plug in the rate. And I could do this for, at this point I can use any trial. I just use one trial. So I'm using the first trial. So I have the rate divided by the initial concentration of NO2 to the second power, because n is 2, the initial concentration of CO to the 0th power, because m is 0. I solve for it, and it turns out the rate constant is 0.21. Now, because I have 4 trials, and each trial will get me k, I could solve for k for each of the trials. And in fact, if I do it in this case, I get 0.21, 0.205, 0.208, 0.206. So if I round to 2 sig figs, it's 0.21. So I get the same answer, which is good. The rate constant should be the same for the reaction. So this is the method of initial rates. Note, that's not really tricky, but I do have to be attentive to which trials I'm using, and it's going to take 3 different runs, because 1, I have to find the order of the first reactant, then I have to find the order of the second reactant, then I have to find K. And if I had 3 reactants, I need 4 steps. Find the order of the first reactant, the order of the second reactant, the order of the third reactant. When I had all the orders, then I could find K. So a little bit lengthy, but after you understand what you're doing, not that bad. And an alternative model is I can use logs. I could do that same information, the ratio of rates, and solve for it using the raw logs. But another thing is that if I have either I have just a 1 reactant reaction, or if I do some tricks experimentally so that the other reactant concentration stays the same over time. This is not doing 2 initial concentration changes. This is, I would keep the other reactant the same the entire time. One way to do that is if I use an extreme excess, even though it's getting used up a little bit, overall it's not changing in comparison to the other reactant. Either way. Okay, so if I take the log of this reaction equation, I end up, and then I play around with my log math. Remember, if I have the log of a product, it's the sum of the logs. If I have the log of an exponential, or something raised to an exponent, the exponent can be multiplied in front and pulled out. If I do all that and rearrange it, I get that the log of the rate is equal to n, the order of the reaction for that reactant, times the log of the concentration of that reactant plus the log of the rate constant. Note that this format, a variable equals a constant times a variable plus a constant, is a linear equation, y equals mx plus b. If I do this and I take multiple measurements of the rate over time with different concentrations, so I left at multiple times in the reaction, I measure the concentration of the reactant and I measure the rate. We could do that if I had a concentration versus time graph. I could, take the rate at each time by taking the slope of the tangent line. So it's a lot of work to get this data, but once I have the data, I take the log of the rate, I take the log of the concentration, I plot them against each other with the log of concentration on the x-axis and the log of rate on the y-axis, and I need to use those because in this equation, the one that's by itself, the y, is the log of the rate, so that needs to be on the y, and the x is the log of the concentration. Now, when I'm done, I find the slope of this line. The slope is equal to the order. So the slope of the graph will be the order n for that reactant. And then the y-intercept, remember I can solve and find then the y-intercept. The y-intercept is equal to log k. So I do a little math. That means the rate constant will be 10 raised to the y-intercept. So this is a different method. It works. It takes a lot more calculations, and sometimes people get lost along the way. But actually, it means, and I only have to do one reaction. So that's the advantage of it.